Now, in the last presentation, we discussed and described what we meant when we spoke of the tangent of an angle. And let's just recap on that. In the case of a right angle triangle, and let's see if I can draw one here. Gosh, that's not hardly even a triangle, is it? Like that, where this is a right angle, and so we might conceive of this as being the horizontal, and this, wiggly though it is, gosh, that's even worse, as the vertical. Then this angle reflects the slope of this surface here. This might be a hill, for example, and let's call that angle, as we did last time, the angle theta. And what we said is the tangent of the angle theta, which we abbreviate to tan theta, is equal to the length of this side, which we'll call h, and this side, which I will call for the moment L. So tan theta is equal to the length of h over the length of L. Now let's just consider, we can scale up this triangle. We're thinking here, when we talk about tan of an angle, the tangent of an angle, we're talking about the ratio of the vertical drop on the slope of the slope and the length along which that drop occurs, without regard to the actual nominal amounts, the actual number of feet vertically, or whatever the unit of measurement may be, against the number of feet along may be. And we'll notice that if we scale up a triangle, let me just make that a little bit bigger. The tan has just disappeared off the screen. But if I make that bigger, the H is bigger than it previously was, the L is bigger because the picture is bigger, but the ratio of H to L, the relationship among H and L, this value of H and L, so long as theta remains the same, remains the same. It's invariant under scaling up or indeed under scaling down. You'll notice in this right angle triangle, let me just draw it again here, that this angle theta has, and this is the right angle, I've drawn it with a little box there to signify that it's a right angle, rather than like the angle that occurs in the corner of a square. Now this H is opposite this angle theta. So we call that side of this triangle the opposite side. And you'll notice this side adjoins the angle theta, and we call that the adjacent side relative to this angle theta. Now this one, this slope, which is opposite to the right angle, is called, now this is a rather funny word, isn't it? The hypotenuse. Hypotenuse. So we have the adjacent, the opposite, and the hypotenuse. So another way of expressing the tangent of this angle theta without these abbreviated letters is simply to say that the tangent of any angle theta in a right angle triangle is equal to the length of the opposite side divided by the length of the adjacent side. Now, let's just take a look at some other ratios. Remember that I said that the relationship between these sides is invariant under scaling up. Now, we can define other ratios that are invariant, just as the tangent, the ratio of opposite over adjacent, is invariant under scaling up. So we might talk of other ratios. What about opposite over hypotenuse? And what about the adjacent over the hypotenuse? I'm going to abbreviate hypotenuse to hype there just to save writing it out again. Well, we have names for these too. And specifically, we refer to this ratio, the opposite over the hypotenuse, as the sine of theta. That's S-I-N-E, theta. That's just a ratio, and we refer to this, the ratio of the length of the adjacent side to this angle, theta, to the hypotenuse, as cosine. Cosine of the angle theta. So now we have tangent of an angle, the sine of an angle, and the cosine of an angle defined